Good morning, good afternoon, good evening to people around the world. This is Martin Hubel, your host of the Db2Night show. And today we have a very special guest with us for our 103rd show on Db2 on Z. Craig Mullins is here with us. Craig, how are you doing today?
Doing great, Martin. Glad to be with everybody here.
Yeah, it's great to have you. We're excited for what you're going to say. And so let me get the housekeeping out of the way so we can turn things over to you and get on with things. Here's our normal get involved stuff. We have a hashtag Db2Night. I try to use that hashtag when I make posts. And we also have a LinkedIn group, which isn't really new anymore. So I'm going to take that word off if I remember eventually. But you can join that, and occasionally we get suggestions in there that are worth looking at. Here's our disclaimer. I could read this, but I gave up reading it a couple of years ago. After you've done it for 8 years, it seems like it's always the same. But I've updated the copyright to be 2020. That's the big change. The rest of it is we're recording it. You'll be able to get the replay. Craig has graciously made his slides available, and I'll put those on the replay blog as well. The replay blog is off the DBI site, as always, where you can find replays and things like that. You can download them. You can watch the show on YouTube. You don't care to do a download. So here's our standard format, quick announcements, our polls, and then we have the Craig's presentation. Okay, upcoming shows. I have not updated the DBI website to allow you to register for these shows. I will do that, I promise, over the weekend. Our next show will be Db2LUW. It'll be Dale McInnes from IBM Canada, which is alternatives for Db2 resiliency. And then Toby Haynes is going to talk on PureScale, and then Carrie Romanoff is the lead architect on Db2LUW. She'll join us on April the 3rd. So we've got a strong lineup of shows coming up there. I also have a show for May, June, which will probably be yours truly, doing my presentation that I'll give at IDUG, and I'll fill in one of the slots there. On the Z side, seeing as we have a Z audience today, the next show is Hakan Roberts of IBM Silicon Valley Lab, speaking on Db2 for ZOS utilities, hints, and tips. Hakan has been doing that presentations on utilities for years. He's well known, and it's a great it's a coup for the Db2Night show to have him come. He's also taken over the role from Jeff Jostin. Jeff Jostin, who is the main architect on Db2 for Z, that is now Hakan as well. He says things hadn't changed that much from the last time since Jeff did the last show, so he said he would rather speak on utilities, and I said absolutely. Then Julian Stuhler from Triton in the UK will speak on DevOps for DBAs in March. And I also should note that the date for Hakan was initially published as February 21 when I was looking for a speaker. Hakan wasn't available that week, so we moved the show 1 week, so it'll be on February 28th, just so you know. On March 20th, we have Julian Stuhler. Then we have our annual All About IDUG show, where the IDUG Conference Planning Committee will join us on the show to tell you why it's worth your time and company's money to go to Dallas in the first week of June to attend IDUG. On May 15th, we have Mariella Wyrock, another IBM Distinguished Engineer. I don't have a topic for her yet because I've not bugged her for it. And Dave Belke will be joining us on June the 19th to complete the year on that platform. So there you have it. We've got another good year of Db2Night show coming up. Also, as always, DBI is our primary and founding sponsor of the Db2Night show, and they have a link that you can follow to see a demo of the DBI products, and that's available on that URL as shown there. If you sign up and watch the demo, they will send you a gift card, which is rather nice of them. So if you haven't seen it and want to, there it is. Upcoming things at the end of this month, or sorry, at the end of next month, around the 31st of January, I'll be teaching a DB2 LUW DBA class through Themis, and that is available through themisinc.com. You can see further details on that class. Also, our winner from last month is Charles Ullery from Burlington Northern Santa Fe Railway. I just wanted to let you know I knew what that acronym meant. And great that BNSF, they've always been a heavy DB2 user, and it's nice to see Charles won that. I also, as a host of a show, I wanted to share a bit of sad news and remember somebody that influenced me early in my career. I took a class from Don Rubb in 1979. That was before DB2, of course. It was a class on communication skills, and later, a few years after that, she started teaching DB2 classes at the IBM Education Center here in Toronto. And after she left IBM, she also served on the executive of the Central Canada DB2 User Group. I'm trying to remember if she had a role with IDUG. I'm not sure on that, but she recently passed after an illness, and it's sorry to see her go. She certainly was a good friend of mine. And if you want further details on that, they'll be published in the Saturday papers here in Toronto, or you can contact me. And here is our sponsors, namely, as I mentioned earlier, DBI, our founding sponsor, and yours truly, Martin Hubel, is the other sponsor of the show. And with that, we are now on to our polls. So let me launch the polls here and get this underway. Just asking what's the highest version of DB2 you have in production. Oh, we got everybody voted, so let me close that and share the results. And we have 11% of our audience on version 12, function level 500 or higher. Still got 2/3 of our audience still on version 11. All right, let's move along and do the next one. I put this in just for grins. I wanted to see how familiar people are with Craig Mullen's books. How many books have you written now, Craig?
Well, 3 titles. The first one, DB2 Developer's Guide, has 6 editions. The second one on database administration is in 2 editions, and the latest one that the presentation today is about is only in its 1st edition.
Oh, okay. Cool. All right, we have that. We'll close that off and share the results there. And well, over half our audience knows of you and has read your book. That's fantastic. And the last one, how many years have you worked with DB2? Just to give us an audience experience level. We do this one occasionally, not every show, but to give an idea of, we've got some old people and new people. That's always fun to know. This will be my 35th year of working with DB2. Oh my goodness gracious. I have played trombone longer. Put that out there. We'll close that poll off and share the results. We see we've got about half the audience is really experienced, and we have some new people as well, and that's great to see. Good. All right, with that, I'll hide that, and we'll go back over. You should be seeing my screen now. And the next thing I'm going to do is you should be seeing a picture of yourself there, Craig.
Yes, indeed.
And I will now make you the presenter. And there you go. As soon as you accept that, you'll be back in control and we can listen to your presentation. Now, to let you know, I will be monitoring our question queue. And if any questions come through, I will break in and let you know what the questions are at an appropriate point.
Okay.
And
can you see my slide?
I can see your slides. They look great.
Great. All right, well, let's dig in. I've got, this presentation has 84 slides. So there's no way we'll be going over all 84 slides today. So some places I may skip around, but the session is based on my new book, as I mentioned. The book is called A Guide to Db2 Application Performance for Developers. Here's my contact information. We'll go past that quickly. So let's see. This presentation is really geared to application developers, programmers, and coders. It's not from a DBA perspective. It's really talking about what you can do as an application developer to build performance into your programs from the beginning. The way I like to talk about it is, if you follow these guidelines, both in the presentation and in the book, your DBAs are going to love you because there's less work they're going to have to do. So we'll look at the first 21 or so chapters. There's a total of 29 in the book, and let you know what the remaining 8 chapters are about. You know, if you were interested in seeing more about the book, this URL here, the tiny URL, will take you to the information out there on the book. So the first 21 chapters outlined here, we'll be going through quickly in the presentation today, starting at defining performance and working through some SQL tips and guidelines and hitting all these other areas along the way. So first of all, in the upper left section of the slide, I'll note when we change chapters. So we'll start with chapter 1. There'll be slides that are associated with that. When I change a chapter, you'll see in the upper left slide that it's moving on to the next chapter. And those chapters correlate to the chapters of the book. And what we're going to do is start here talking about a definition of database performance. I mean, if we're going to strive to ensure that we have database performance in our applications, then we really need to be able to define what we mean by database performance before we move on. So a lot of times we have this concept in our head, I have an idea of what it is, but without a firm definition. So what I say database performance is defined as the optimization of resource use to increase throughput and minimize contention, enabling the largest possible workload to be processed. And if you look at this slide, each of the 4 highlighted sections are outlined in a bit more detail on the slide. I'm not going to read through it, just at a high level. Workload is the things we're trying to do at one time. Throughput is the capacity of the machine to process that workload. Resources are the things at the computer's disposal to process that workload. And contention is when 2 or more components or resources are conflicting with one another. And all of these things work in tandem to deliver database performance. Now, additionally, when we talk about database performance, there are 4 areas that can impact the performance of your database system and applications. There's the application itself, the database and structures, the subsystem or instance, and the environment in which they all run. Now, this presentation is just going to focus on the first aspect. Another thing I want to mention as I move through the presentation, this presentation was built, as is the book, for both ZOS and LUW. I'm really focusing only on the ZOS stuff here. There may be some things in the presentation that are LUW related that I will ignore or not really reference, but the book is for both and mentions the differences between both. So keep in mind that assuring optimal performance is complex, and by making our applications sensitive to performance issues, then developers can minimize the headaches of others because they can focus mostly on the other areas. The DBAs, the sysprogs, are going to look at your database and the subsystem and the other environmental aspects of performance because the developers have really baked performance into the application. Now, the other aspect of performance that I like to bring out right at the front is that there are 3 primary aspects that impact the performance and cost of your database applications. And these things are CPU usage, IO usage, and concurrency. Please take note of the arrows here and the direction they're pointing. That's important. What we want to do to improve performance is decrease CPU usage, decrease the number of IO operations, and increase overall concurrency. And if we're not doing at least one of those things, we're probably not really helping out with performance. Yeah, we may be making a change, but it's not going to improve performance. Basically, fewer CPU cycles are going to translate to work being done quicker. And when the same amount of work is performed using less IO, costly disk operations are eliminated, and that improves performance. And concurrency, if we are eliminating conflicts between our resources and programs, then more work can be done at the same time in parallel instead of sequentially. And that too can reduce the overall time to complete a task. So as you are thinking about performance, and as you're thinking about the way in which you build your applications, keep these three aspects in mind: CPU, IO, concurrency. Decrease CPU, decrease IO operations, and improve concurrent operations. Okay, moving on to Chapter 2, Encoding Relationally. The folks who've been with DB2 for a long time understand this, but it's good to get a reminder, and it's good to, as you bring people into the fold of a relational database system, DB2 for ZOS, that we need to be coding differently than we do with flat files. Even if you're a fantastic programmer in this flat file world, there are things you have to learn before you can efficiently code DB2 applications. You access a relational database differently than flat files because the database is not a set of files. Files have no relationships set within and among them, whereas the database does. The records are interrelated. Additionally, new programmers will often think that a table is a file, but that's wrong thinking as well. Tables are not file. Tables are based on sets. Sets are not ordered. Members of a set are all of the same type. And when you perform an operation on a set, the action happens all at once to all the members of the set. And that's not so with records of a file. And rows are not records. Records are sequential, but rows have no physical order, at least conceptually. Yes, back in the back end physically, they are actually stored in some order out there, and that can impact performance. We'll talk about that later. But conceptually, the rows are not in any sequence at all, and you should code that way, thinking that way. And finally, columns aren't fields. Columns are typed, meaning that if it's numeric or say it's integer, only integers can be stored in that. Whereas, with a data set, and you have a field, you can store anything in there, and if you store the wrong thing when you're expecting a number, you get an error. Well, DB2 won't let that happen. Additionally, columns can be null. That isn't the case for fields. Without a program, a field has no meaning at all, whereas the DBMS gives meaning to columns and the way in which they're typed and their nullability. So essentially what I'm saying is in the relational world that there's more metadata, and that forces meaning upon the data and the way in which the data should be accessed for efficiency. So keep that in mind. This means unlearning the flat file mentality. Application developers who are used to processing data a record at a time need some training to start accessing things a set at a time. You should not be duplicating flat file processing techniques if you want to optimize the performance of your applications. Learn to join instead. If you don't know what I mean by master file processing, this is where you open up a file, read a record, open up another file, and access a record in that new file using the data you just read. So, we open up this file, get the key to open up another file. Instead, join on those in SQL, and it's going to outperform a program join. Also keep in mind that opening a cursor is not the same as opening a data set or opening a file. There's a lot that goes on behind the scenes when you open up a cursor. It's not always going to read all the data, but it depends on many things. And if you're sorting, that's a big deal too. So the relational world differs from the flat file world. You need to keep in mind modification and how we issue a modification statement can impact lots of data. Remember, I said things happen all at once in these sets. Well, if we forget a where clause, and look at the SQL statement here on the left, delete from emp, we just deleted the entire employee table. We want to make sure we code the right where clause. Here we're saying where emp number is 10. Of course, if you have a cursor open and you say delete from emp where current of cursor name, you're only deleting the row where that cursor is positioned. So a lot of times programmers are used to that. They issue the delete, they don't have a where clause, just where current of cursor, and then they think, oh, well, delete from employee, I'm only deleting, and they forget the where current of cursor, and everything goes away. So take care, make sure that you're issuing your modification statements with a where clause, whether it's a where the column equals a value or where current of cursor. And these two rules on this slide should always be at the top of your mind as you write DB2 SQL statements. You always want to return the smallest amount of data possible to accomplish your task. Now, I almost never say always or never, but here's an always. Always retrieve only the smallest amount of data. Again, that means using a where clause to minimize the number of rows, and only requesting columns that you need to process in your select list. Now, sometimes you see avoid select asterisk. That's good advice for a lot of reasons, like insulating your program from change, but it's not the entire best practice. The rule of thumb, the best practice should be that we're listing only the columns in the select list that we actually need to process in the program. So here's an example. What's wrong with this SQL statement? Well, nothing from a syntax perspective, but we're violating the rule we just talked about. We're asking for columns that we already know the values of. Because we have a where clause, this is where job code equals A, there's no reason for us to list job code in the select list because we know it's only going to be equal to A. Same with department equals MIS. Every column added to that select list adds overhead. Yeah, it's a small amount of overhead, but it can add up. Think about that SQL statement running hundreds or thousands of times a day, or maybe even more. That little amount of overhead turns into a lot of overhead. So code from the start, only asking for what you need. When you're coding predicates or where clauses, make sure that the host variable and data type and length match the data type and length of the column. Or if you're comparing two columns, that the data type and length of each match. If you don't do this, DB2 is going to have to consume some amount of CPU. And again, we want to be reducing CPU. And it has to do that to make the two arguments able to be compared. Now, in past versions of DB2, if you didn't do this, it would immediately degrade your statements to stage 2. And we'll talk what I mean by that later in the presentation. That means it's going to be less efficient. That's no longer the case as long as you're within the same data type family. So character to character, numeric to numeric, like integer to decimal. You can still do that and it won't get degraded. Now, you're still going to have the CPU overhead, again, a small amount, to DB2 has to do to make them comparable. So matching data type and length is still a good idea. Chapter 3. We want to pass through the data the smallest number of times possible. Accessing the same data over and over again consumes more resources. So you should code your program to avoid issuing the same SQL statement over and over again, whenever possible. Sometimes you have to do it, but if you can avoid it, avoid it. Here's an example. Sometimes just looking at things a little bit differently can improve performance. On the left, we see two SQL statements, and they can really be combined into one SQL statement because they're accessing the same data from the same table, and it's almost the same thing except for the last predicate. We're looking for sex equals to female, and the second one's looking for the year of the hire date being 1999. Well, if we combine the two together like we see on the right, DB2 can do that with one pass of the data. Now, you're going to have to code your program differently because the data is going to come back intermixed. And if you're only processing females for one thing and hire date for another, you're going to have to be able to, as you read the data, send it off to the right area to be processed. But you're minimizing I/O by passing through the data once. Another possibility, there's many possible ways. Here's one that takes a union and converts it to a case statement. You see on the left-hand side, we're going after systables, looking for tables, views, and aliases, and then unioning them together. Well, instead of three separate statements combined with union, we can pass through the data once and indicate table, view, and alias in our output in the select list, and that can potentially be more optimal. Now, of course, the optimizers are getting more intelligent about being able to rewrite queries to obtain optimal access paths. So certain ways that you reformulate things may not matter, but you can try to coerce it by combining these things together to make one pass SQL statements that look at the data once instead of going through them multiple times. Now, case statements, sometimes people don't think about them in various contexts, and maybe you only think about them in a select list or in a where clause, but you can use them anywhere that an expression can be used in your SQL statement, not just limited to reading data. So, here's a quick example. We have a requirement where every employee with more than 18 years of education is to get a 1% raise. Generous, right? But some departments have decided to give different raise amounts. One approach would be to code separate update statements for each requirement based on the employee's department. But you could more efficiently use a case expression that passes through the data once, giving the appropriate raise based on the employee's level of education and department. So you can see here, you've got, when the department is A01, you get a 5% raise, C01, 2.5% raise, and so on. And if you don't fall into one of those departments, you get the standard 1% raise. And this can be accomplished with one pass through the data. So the more we pass through the data only once, the more efficient things become. Chapter 4. Avoid black boxes. Black boxes where you've got this data access routine. And instead of writing SQL in your application programs, the SQL is put into this black box, and every program calls the black box for data. This usually is a management fiat where they say this is what you have to do, but it's generally speaking a bad idea. It shields developers from having to know SQL. And that's not a good idea. And the tendency is that shortcuts get taken. Shortcuts that basically avoid all the things we just talked about in terms of writing effective SQL. It inevitably is going to deviate in some way from the guidelines we just talked about. All of Chapter 4 is about this. I've also got an article out there that you can go to the URL at the bottom of the slide, read more about it, or you can go to the book and read more about it. Here's the reasons for avoiding that. The shortcuts that I talked about. For example, if you've got two teams and they're both wanting to get customer information, but this team 1 only needs 5 columns and team 2 needs all 38 columns. but everything else about the SQL is the same. The shortcut mentality is going to be, well, let's return all 38 columns in the black box, and team 1 will only get 5 of them, and team 2 will get all 38 of them. Well, you just built bad performance into your application by design in that case. So, but to avoid writing extra code, those shortcuts generally get taken. Extra code means more work, and you've got more code, because you're calling a program and you got to get to the right code in the calling program, you got to send the data back. That's all work that can be eliminated if you don't have the black box. Ignorance of SQL is not a good thing. You want your developers to understand SQL and what's going on behind the scenes, because then they'll be more knowledgeable about how it's going to perform. The black box is essentially a new access method, but SQL is already an access method and is very flexible, and you can do a lot with it, so why write another access method? And then also the black box becomes a single point of failure. If the black box fails, every program using the black box can no longer get data because the black box is out of service. So lots of good reasons to avoid black boxes. Chapter 5, Code for Concurrency. Concurrency is one of the 3 major factors we talked about. CPU I/O concurrency.
I found this on the web.
And a lock management system is required to provide concurrent access. Now, DB2 supports locking at various levels or granularities, at the table space level, at the table level, the page, the row level, and depending upon the way in which the database is implemented and the way in which the parameters have been chosen by the DBA will impact the type of locking that happens. But what programmers need to understand is the things they can do to minimize the impact of concurrent access problems. The first thing to consider is the lock timeout. In order to take a lock, DB2 is going to go out there, it's going to look at the data and see if there's any incompatible locks out there. In other words, if someone else is trying to modify it, they're not going to let you modify it at the same time. A timeout occurs when DB2 waits too long for a lock. Another process is holding that lock. When your request times out, it's either going to fail or you have to rerun it. Or the request can be issued again if you've got retry logic coded into the program. Generally speaking, timeouts are going to increase wait time and reduce concurrency. When you experience a timeout, that means another process is holding a lock on the data that you're trying to access, you're trying to modify. So what we should be looking to do is minimize the duration of locks. We want to hold locks for the shortest period of time. I'll give you some advice on how to do that in a couple slides. Another consideration of concurrency, of locking, is the deadlock. This slide shows the deadlock, or the deadly embrace. A deadlock happens where competing processes each hold a lock on the resource the other process wants. What we see here in this example is process A has a lock on page 3 and wants page 7. At the same time, process B has a lock on page 7 and wants page 3. You can see how they're both going to wait forever unless something happens. So in order for workload to continue processing, one of these processes, A or B, has to be terminated so the other can proceed. And there's components of DB2 that do this deadlock detection and terminate the process with a shorter amount, with a smaller amount of resources that have been consumed to that point in time. But you want to be avoiding these things, even though DB2 will find them and take care of them for you. Okay, so the advice. What are some tactics to optimize concurrent access? Well, we want to minimize deadlocks, and the way you can do that is by coding updates in the same sequence for all the programs accessing the data. So from our previous example, if both process A and process B were to access page 3 and then page 7, the deadlock wouldn't occur because process A would get page 3 and then 7, do what it needed to do, and process B would get page 3 and then page 7. Wouldn't get 3, 7, 7, 3 and have that problem. Now this means you got to change the way in which you're writing your code because obviously the order is differing, but you know, that's what programs are for. You can write them to do what you need them to do. From a timeout perspective, another technique we can use is to issue modification statements, inserts, updates, deletes, as close to the end of the unit of work as possible. In other words, as close to the commit as possible. The later in the unit of work that the update occurs, the shorter the duration of the lock is going to be. And the shorter the duration of the lock, the less chance that you're going to time out another process waiting to process what you're doing. We can encourage lock avoidance. With lock avoidance for read-only cursors, if you bind your programs with isolation, cursor stability, and current data no, then lock avoidance can happen, improving concurrency. We'll talk more about isolation levels coming up. Lock table, you might be able to use lock table to help things out. If you say lock table, then at the beginning of your process, no other page or row locks are going to be taken because the table lock is taken at the beginning and it locks everyone else out. But be careful because that basically is saying there is no concurrency. No one else can access this table while I'm going after it. If you know for a fact you're the only one going after the table, using lock table will be more efficient because you don't have all the additional locks being taken. But be very careful before you use it. You can consider isolation UR, uncommitted read, also known as dirty reads. And that can avoid locking, but you have to be careful here too. We'll talk about that coming up. And you should exercise caution if you're using tools that auto-commit, things like Spoofy or Toad. Developers sometimes disable auto-commit. And they do that because they want to iteratively test, roll back changes, tweak, test again. And that type of testing is fine, but be very careful. If you leave things uncommitted and then go out to lunch, or even worse, go home, then the tool still holds locks that it needs, blocking others while that tool is active. Now, if you're doing testing on your own tables and no one else is accessing them in a test environment, not as big a deal. But if you've got shared test tables and you do this, you're quickly going to become a despised developer. Next, from a concurrency perspective, we want to avoid bachelor programming syndrome, which everybody knows is fear of committing. Every program that modifies DB2 data should implement a commit strategy. That strategy should only rarely, almost never, be to avoid issuing commits and let the end of the program cause the modified data to be committed. Only very small programs that run for very short durations should even consider that approach. And even then, it's probably wise to clearly document in the program why there are no commits being issued. So you want to, after so much time, do a commit that frees up your locks, and it's going to minimize timeouts and deadlocks. Generally speaking, if you're getting these timeout errors, lock timeout errors, you probably can find a program that's running for a long period of time, making a lot of changes and not committing. And the programs that are failing because of lock timeout are not the ones that are causing the problem. It's the one that didn't issue the commits. So be very careful about this. Be a good steward of database change, code commits into your application. Okay, chapter 6, locking and isolation levels. We'll delve a little bit further into locking and isolation here. This slide shows a sequence of events, which I'm not going to read through now, but basically it's saying that if we don't have a lock mechanism you're going to have data integrity problems. As people try to read data while the data is being modified, or two people trying to modify it at the same time. The locking mechanism of the DBMS avoids these type of dirty data problems. So you need to understand the isolation levels that are available to you when you bind your programs. What is isolation? It's a component of ACID. ACID, you probably have heard about that in databases, showing that you can have changes happening to the data while other changes are happening to the data, and each one looks like it's happening at the same time. So isolation is the I in ACID. To achieve this, again, locking mechanism is needed, and there are various types of isolation that can be chosen. Each DBMS offers different ways to do that. In DB2, we've got 4 isolation levels, and these isolation levels can be specified either at the program level or at the SQL statement level. If you specify it at the statement level, it's going to override the isolation level set at the program level, but only for that statement. Okay, here's the next few slides. We're going to quickly discuss what these are. CS, or cursor stability, is probably a reasonable trade-off between data integrity and concurrency. With CS, read-only page locks are released as soon as another page gets accessed. So if you're using cursor stability, your transaction is never going to read data that has yet to be committed. Only committed data is going to be read. Locks are going to be released as each new page gets accessed. But keep in mind, if you're using cursor stability and your program tries to read the same data twice, which we already said probably not a good idea, but if it does and you need to do that, then there's no guarantee that it's going to be the same data, because someone may have gotten in and modified the data in the interim. The next is repeatable read, or RR. In this case, all page locks are held until they're released by either a commit or a rollback. So you can see how this is going to reduce concurrency, because you're holding locks longer. Not when you go off the page, you're keeping them until you issue specifically a commit or a rollback. But it might improve data integrity. With RR, it's useful when a program requires consistency in rows that are accessed twice during the execution of the program. Read stability, similar to repeatable read, but it's not quite as stringent. A retrieved row or page is locked until the end of the unit of the work, so in the commit or rollback. So no other program can modify the data until that unit of work is complete, but other processes can insert rows that might be read by your application if it accesses the row a second time. So if you're using read stability instead of RR, you only want to do that if you can handle retrieving a different set of rows each time a cursor or even a singleton select is issued. You want to make sure with read stability that your application is not dependent on having the same number of rows returned each time. And then there's UR, or dirty read. Locks are avoided completely when using UR. So it can help to overcome concurrency problems, but at the cost of data integrity issues. When you're using an uncommitted read, an application program can read data that's been changed, but it's not yet committed. It boosts performance because you're reading data without taking locks. However, you might read data that never was in the database. You're going along, you're reading against table A, someone at the same time is inserting 100 rows to table A. You keep reading, eventually you get to those 100 rows, you read them. The program that inserted them says, oh, wrong rows were inserted, roll back. You read data that never was in the database. So UR can be a nightmare. If you're dealing with balances or ledgers, UR is not a good idea. Even if you're reading data, produce a report. If you expect that report to be 100% accurate at all times, UR is not a good idea. In my experience, what I've seen is dirty reads, UR, are used altogether too often in DB2 shops. I've seen organizations where the standard is to add with UR to all select statements, and there's little concern about the possibility of impacting data integrity or data accuracy. That's not a good thing. These things can run maybe for a while without any problems, and then all of a sudden something happens that, like I just mentioned, we do a rollback, and then we wind up messing up the database. So the general rule of thumb is avoid UR when the results have to be correct. And when shouldn't the results be correct? Well, you might have examples where maybe you're doing an average of millions of rows. In the example I showed where you've inserted 100 rows, is the average of 1,000,000 rows going to be that much different than the average of 1,100,000 rows? Maybe not. So, doing analytics, doing those types of things, maybe some dirty read processing is good, but it generally doesn't belong in production programs where the data needs to be accurate. Okay, before moving on from these, the one thing I want to mention is, as a programmer, what you need to keep in mind is the choice of isolation level can cause your program to run and operate differently. No code changes other than binding with a new isolation level, and different rows may be returned based on the isolation level that you've specified. So keep that in mind. Chapters 7 and 18 are basically ideas about avoiding writing code. What we want to do is we want to avoid writing code whenever we can, and instead use Db2 operations to do it. Some examples: loading, unloading, instead of writing your own load and unload programs. Functions, stored procedures and triggers, merge, select from insert. The more we can do to avoid writing code and consolidate, the better off we're going to be. Thinking about functions, there are many built-in functions that you can use to simplify your coding efforts. This is only a sample of the functions that are out there. There's different types. Scalar functions basically convert a value. Column functions over over a number of rows. We'll say what's the count of rows, what's the average of a value. Those column functions operate on more than one row. Date time functions, converting your date and time. All of these can be used to reduce the amount of code that you write. So go to the manuals, understand what functions are there, and use them instead of trying to write your own code to do similar stuff. Probably the most important thing you can do to optimize performance is understand the indexes that are out there. How does an index work? Well, DB2 index is a balanced B tree. When you index a table by one or more of its columns, you can access data directly and more efficiently because the index then is ordered by the columns to be retrieved. So here's an abstraction of what a B tree index would look like. 3 types of pages: the root page, the non-leaf pages, and the leaf pages. You always start at the root. Well, not always, but you generally start at the root, go through the non-leaf pages, out to the leaf pages, where the leaf pages point to the data. And it uses pointers or record identifiers to uniquely identify a row in DB2. So if we can consider a table here with maybe a reasonable amount of rows, say 150,000. If we want to get the row in that table that contains the index value 63, we would only need 4 IOs. So here we go through the values, root, non-leaf, leaf, down to the actual page, as opposed to scanning the thousands of pages in the actual table. So we can see how that index reduces IO. So you need to know the indexes available to you as you write your SQL so that your program will use indexes whenever possible. The book has queries for both ZOS and LUW that can be run to show you when indexes are available. Ask your DBA for help too. Maybe you don't have access to the catalog tables or are not comfortable with that. DBAs can help you by getting lists of the indexes that are available. Chapter 9, data clustering. There's multiple meanings for the term clustering when it comes to the DBMS. But here I'm talking about how data is stored on disk, the way it's physically stored. And that can impact the way you write your SQL queries. Clustering is used to control and sequence rows on disk stored contiguously by the key values in that index. And there can only be one clustering sequence per table. Physics, data can only be stored in one sequence. So you can see how clustering the data can be more efficient than accessing the same data in an unclustered table. For example, if we're saying select from table where a value is between 7 and 11, the top clustered, we're just going to one data page. Whereas if we go to the bottom, we see 7 is over here in the far right, 11 is in the far left. We're going to multiple data pages in an unclustered table. So clustering, if we're going after ranges, very good for performance. This example is really simple. We're showing clustered accessing it on one page, unclustered on two. If we've got hundreds or thousands or hundreds of thousands of rows, you can see how clustering can significantly reduce I/O. Chapter 10, optimization. The accessing data in a relational database system like DB2 is going to differ significantly than a flat file, a traditional type system. When accessing a file or a data set, the programmer is deciding how and in what order the data gets accessed. But with SQL against DB2, the DB2 optimizer is going to decide the data, how it gets accessed and in what order. You tell it what you want, not how to get it. It doesn't matter how data is physically stored. If indexes are removed, DB2 can still access the data. It's going to be less efficient. If a column is added to the table, the data can still be manipulated by DB2 without changing the program code. And that's all possible because the physical access paths to DB2 data are not coded by the programmers, but are generated by DB2. In the older legacy systems, VSAM, IMS, flat files, the programmer had to know the physical structure of the data, had to know if there was an index, and had to write appropriate code so that the index would be used. If you remove the index, then the program doesn't work. But this flexibility and physical data independence is there because of DB2's optimization capability. So what is the optimizer? It basically works like an expert system, where an expert system is basically a set of rules, and when you combine those rules with data, it returns an expert opinion. Well, the optimizer gives expert opinions on data retrieval for SQL queries, and it's based on the relevant data that it stores in the catalog, the statistics that they get populated with run stats. Generally speaking, that's the DBA's duty, but sometimes developers get into that as well. So it takes the rules, the data, and the query, and renders an access path for it. This shows a high-level visual representation of what goes on with optimization. All this user data, run stats, populate the catalog, then you've got a query coming in. The SQL statement gets ingested into the optimizer. It takes other system information, maybe optimization hints, runs it through the query cost formulas, and out the other end come optimized access paths and plan tables. And I say tables because there's multiple of them now. So anybody who uses DB2, anybody who programs SQL should be able to look at this high-level chart and walk through it the way I just went through it. You don't have to actually know what the optimizer is doing to know that it is the things that it has to do in order to render an access path for you. Okay, chapter 11. Talk a little bit about sequential versus random data. Sequential read starts at a specific page, maybe at the beginning of the table, and reads subsequent pages until no more are required, and that may be the end of the table. A random read goes to a specific page based on a key value, and that usually requires an index to achieve. So sequential versus random access. Now, thinking about this, random access is, we're getting a small amount of data, usually by the primary key, maybe another index key, whereas sequential access is getting multiple pieces of data in sequence, such as a range of customers or a range of employees' names or a series of numbers. Which is going to benefit most from clustering? And we talked about clustering as putting the data in sequence on disk. Well, sequential access is most improved by clustering. Random access, not so much. If all we need is to get in, get a row, and get out, it doesn't much matter if the data is clustered, right? It's just going to go to a different page, perhaps. Whereas if all the data in a range is on a single page or pages located physically next to each other, then we're reducing I/O. And remember, minimizing I/O improves performance. So from a sequential access perspective, clustering is important. There's a table and table space scans. It's a simple access path strategy. This is, the optimizer can generate that for you if there's no valid index, or maybe if the data is small enough. A scan is going to read every page, examine each row on the page, figure out if it satisfies the query, return only those rows that do. Sequential prefetch can be added into that. That's a way of gathering a bunch of data before you need it. Sequential detection can kick in if it didn't think we'd need prefetch at the beginning, but it turns out we do. Prefetch is turned on at bind time, sequential detection, runtime turning on prefetch. Generally speaking, we want to avoid table space scans unless you really need all the data. It doesn't have to be in any particular order, or if there's a small amount of data. Here's a sequential prefetch and detection and why it can help. A single I/O, normal I/O, is only going to occur one page at a time, but up to 32 pages at a time with prefetch can happen. So if we're reading page 1 and we prefetch, after we've read this, DB2 goes out and starts reading all the rest of these pages while we're operating on page 1. The next one, as soon as we need page 2, because we're accessing data sequentially, it's in the buffer pool. We don't need to go out and wait for the I/O to happen. So that's why prefetch, detection, good things. Indexed access, there's all different types of indexed access. Generally speaking, we want to do this to improve the performance as opposed to scans. Direct index lookup starts at the root page, matches values all the way down to the leaf pages to get the data. Matching index scan, predicates are required on at least the leading index key column. It starts at the root page, probes through the non-leaf pages down to the leaf page based on the matching predicates, and then index screening is applied for all the non-matching predicates. When a starting point can't be determined because the first column in the key isn't specified, DB2 can do a non-matching index scan. Not as efficient, but still we're just reading the leaf pages of the index as opposed to all pages of the table space. Index screening is where the matching index scan is done on the leading columns of that composite index, but then applying the additional predicates. We can use sometimes multiple indexes, and it's called multiple index access. If you have an and or an or in your query, sometimes DB2 will choose this. And then there's one fetch index access, which is incredibly efficient. This is used if you're doing min or max function. Very efficient, just get to the one row you need. There's also direct row access. I'm not going to go over this. It's rare, but it can be very efficient if you've got row ID values that you're using for log columns. Joining in an SQL join it combines columns from one or more tables. One table I say because you can join a table to itself. Most joins are done on equality predicate, but it doesn't have to be. It can be greater than, less than, greater than, or equal to, whatever you need. The inner join is the most common type of join. This is going to create a table by combining column values of the joined tables based on the join predicate. So the query compares each row of A with each row of B to find all pairs which satisfy the join predicate. There's also an outer join, and that can be a left, right, or full outer join. And in this case, the join table retains each row on the left, on the right, or both, even if no other matching row exists. In this case, left and right refers to the two sides of the join keyword. I find that sometimes a picture is worth a million words. In this case, I think inner join, just the things that match. Outer join, things that match, plus on the left, things that match, plus on the right, or things that match, plus the stuff on the right and the stuff on the left, where the things that aren't there, when you've got rows from A that aren't there with B, the B values are null. Likewise, we got things from B that aren't there in A, the A values are null. So all of these options are there for joining. Good rule of thumb, make sure you always provide join predicates for all the tables in your SQL statement. If you fail to do that, like we see here, you'll have a Cartesian product. That means every row from every table is joined to every row from the other table without regard to keys or relationships. Not going to perform well, and probably give you the wrong results too. This is a simple example. You can see, there's no combining E to D, but if you've got, 12 tables joined here, it's possible that you missed one of the join criteria. So form these with care. Make sure you've always got a path through all the tables being joined. So in this example, we turn a Cartesian product into not a Cartesian product by adding the where clause in the join. The Db2 optimizer has a series of techniques that can be used to join tables. When more than one table is referenced in the from clause or a join clause is specified, then we're saying Db2 do a join. Db2 will do a series of instructions to combine the data from the tables. Each multi-table query is broken down into separate access paths. The optimizer selects two of the tables, creates an optimized path for accomplishing that join. And it's not going to do this randomly, but it chooses based on what it thinks is going to be the most optimal way to join. The optimizer then continues joining to the other tables until the entire query has been optimized. When doing this, he's going to have to determine the best join algorithm to use. The join algorithm, or method as it's called, defines the basic procedures for combining the tables. There are 3 or 4 basic types of joins that can be deployed: nested loop, merge scan, and hybrid. That's all for Db2 for Z. LUW has a hash join, but it doesn't have a hybrid join. And each of them operate differently. But certain basic steps are common to each join method. The first decision is which table should be processed first, and that's called the outer table. After that, a series of operations get performed on the outer table, preparing it for joining. Rows from that table get combined to the second table, and that's called the inner table. Another series of operations are performed on the inner table before the join occurs, as the join occurs, or both, depending on the access method and what the SQL requires. Although all the joins are composed of similar steps, each of the methods is quite different when you get beyond the generalities. The optimizer understands the advantages and disadvantages of each methods and how that method can affect performance. And generally speaking, does a good job of choosing the right method. It uses statistics and the catalog, it uses system information, and determine which is the best inner, which is the best outer, which is the best method. Considerations, generally speaking, the smaller the table, the more likely it'll be chosen as the outer table. The reason for that is that it reduces the number of times that the inner table has to be reaccessed. Common theme, remember we were talking about reducing the number of passes through data. table is going to be more likely to be chosen as the outer table if you've got selective predicates that are applied, because the inner table is only accessed for rows satisfying those predicates. If it's possible to do an index lookup on one of the tables, that table is going to be a good candidate to use as the inner. If a table doesn't have an index, it's not generally going to be a good candidate for the inner table, because the inner table entirely gets scanned, and that increases the amount of work we have to do. Another consideration is a table with the fewest duplicates is going to be chosen as the outer table in a join. Of course, none of these are hard and fast rules, and that's why the optimizer is an expert system and understands scenarios and situations and applies them appropriately. Okay, this slide, again, enumerates the join methods. If you download the slides, there are several slides of additional details on these methods, but I'm going to skip ahead and get to the guidance slide here. In general, nested loop join is preferred in terms of execution cost when a small number of rows qualify for the join. As the number of qualifying rows increases, the merge join becomes a better choice. The merge join is going to make sure things are sorted and process things in sorted order, one by one, instead of repeatedly looping through the data. In the case of the hybrid join, it's going to fall in between the two, and it's going to depend on other system details such as memory, size of your RID pool, and so on. This slide also mentions a hash join, but I'm not going to cover that here because that's an LUW thing. Overall, basically, these performance generalizations are vague, and your results are going to depend on the exact number of qualifying rows, as well as other factors such as design, organization, accuracy of stats, hardware, and so on. But it's good to know what these join methods are and YMMV. Your mileage may vary. Okay, stages, indexability, and sargability. The general concept of, I'm going to forget sargability, that's an LUW thing. There's a concept of whether or not an index can be used. That's indexability. Is the predicate indexable? If it is a predicate that isn't even indexable, then there's no chance of using an index, even if you create an index on the column that's being referenced in the where clause. Stage 1 and stage 2 are where the predicate gets processed. The earlier stage 1 is more efficient than stage 2. That's because data has to be passed to these stages. The less data that's passed from stage to stage, the more efficient it is. Whether or not a predicate is indexable or stage 1 or stage 2 is defined in the manuals. For DB2Z, it's the Managing Performance Manual. Download it, go to page 359, print that out, and tag it up in your cubicle. Stage 1 better than stage 2, indexable better than non-indexable. I also define stage 3 and 4. These are just my terms. Stage 3 is moving predicates from SQL into your program. So instead of having it in the where clause, you have if then else statements in your program. This is generally bad because more data gets moved. Stage 4 can be thought of as the black box. So 1 better than 2, 2 better than 3, 3 better than 4. Filter factor is basically a ratio, and it's estimating the IO cost of your predicate. And you can use it to determine how many rows are going to qualify for a predicate. Here's a sampling of the filter factor formulas. You see the formula and the default filter factor listed. The default is used if these first key card, high 2 key, low 2 key, these are all database statistics gathered by run stats in DB2. If you didn't gather them, DB2 will use the default, and generally speaking, defaults are bad, but better than nothing. So, for example, consider the query here. What's the filter factor? The column has an index called xemp2. The optimizer will determine the filter factor for the work depth predicate to estimate the number of IOs to satisfy the query. If we can see that the filter factor for this predicate is 1 over first key card, right? Work depth equal 1 over first key card. So in that case, we go and we look in the DB2 catalog, we see first key card is 9. That makes the filter factor 1 over 9 or 0.11, meaning DB2 estimates 11% of the rows are going to be used to satisfy this. The smaller the number, the more efficient, the more DB2 is going to consider. A smaller filter factor more efficient than a larger filter factor. Explain is used for telling you what access paths were determined by DB2. Always specify explain if you're interested in what DB2 is doing. If you don't say explain, you don't know what the access paths are, and you're basically blinding yourself. So always say explain, and you always get the information out there that will tell you the access paths. You may need help going through this for DB2Z. The explain tables are out there in these libraries. Go to your DBA, they can help you walk through creating plan tables for you in your test environment. You can run it not just at bind time, but also explain a single statement. So you can set a query number, put the statement in there, and run it as an explain, and that'll go to your plan table as well, telling you information about the access paths. Now, I'm going through this real quickly. This is a subject for an entire presentation of its own. You really should look at visual explain tools such as the ones in Data Studio or Data Server Manager. Some of the vendor tools have their own visual explain tools. Whatever tools you have available, use them. They're easier than looking through the plan tables. And your DBAs will be happy you want to look at this stuff and figure it out. Parallelism, the general idea here is if we run multiple tasks at the same time, improving concurrency, we can improve execution time. So if we take these 4 that we're running serially and instead run them in parallel, we can see the elapsed time decreases. Skip the LUW slide. The best candidates are IO-bound queries. Here's some examples of what those could be. Okay, I've got stored procedures. We talked about them earlier in terms of a way to avoid writing code. So if you write it once in the stored procedure and call it, you can get the benefits of reusability and consistency and data integrity. Some of the performance gains. Without stored procedures, we get a lot of calls back and forth between the database server and your application, so these network calls can get eliminated if we're doing the work on DB2 in a stored procedure. In general, though, avoid a one-size-fits-all implementation. Sometimes the advice is everything's going to be written in a stored procedure. And again, there's that word everything. Generally speaking, use them where they make sense, but if someone's saying everything, you really need to sit down and figure out why and do a little bit of extra work there. Dynamic versus static SQL. Most of the work these days is dynamic, where dynamic is not, the access path isn't known at runtime. It's not necessarily hard-coded. The SQL statement can change at runtime. And most of the work these days is dynamic versus static. I have a series of recommendations here, but getting close to the end, I'll leave it to you to look through when to favor dynamic over static. And you know, these are the general rules that I follow for that. Chapter 21, the last one we're going to talk about, is writing SQL. Remember, there's multiple different ways you can write an SQL statement. Like, for example, here, we can see the same thing being done, returning the same results in multiple different ways. Sometimes one will outperform another. If you can think of multiple ways to do it, run tests, see what the access paths are, see what the performance is, because even though the results get returned to the same, the performance can differ. Here's another example. In this case, not is non-indexable. So if we get the not out of there and we code it in one of the two ways at the bottom, then that can improve performance as well. Keep in mind, there are some caveats. You have to understand your data. Now, if we're only looking for data that's not between A and G, then we have to make sure that there's nothing before A, or this second one won't work as well, right? All right. Of course, we're not going to have time to go through all the chapters, as I mentioned. Here's a high-level overview of the remaining chapters that are in the book. And I also want to extend an offer. If you go to this URL here at the bottom of the book and you enter either of these codes, Db2N for the print edition, Db2W for the ebook edition, you can get a 10 or a 5% discount on the book. So if what I went through today was at all interesting to you, if you're interested in getting a little bit more details on anything I talked about, head on over and take a look at the book. And also be sure to get the slides because some of them I skipped over. Martin?
I'm here, Craig. I just wanted to point out on your slide there, did you really mean the 2019 or 2020 on your discount date? On your contact
2020. Yeah, the first month of the year, I always do the wrong year. So yeah, 2020.
Oh, good.
Thanks for pointing that out.
You're welcome. It's amazing what can slip by sometimes. I feel that no presentation is complete unless I can find 3 typos in my own work, I mean. So I'll take control back now.
Only 3?
Yeah.
All right.
Any attempt to make my material perfect only results in the introduction of new errors. It's a gift, I figure. Keeps me humble. Or something like that.
That's a good thing.
Yes, it is.
We all need humility.
All right. I hope I made myself presenter, and there we go. Just to finish off, we normally have a bit of a commercial for DBI, and I've gone through these slides in past shows. This is really just the new new interface that they're building for the DBI Performance Suite. I've talked about them before, and of course the demo is available on the DBI website. I also put in Craig's slide there with his contact information and the discount codes again, in case you missed it the first time. And of course that'll be available in his download as well of the slides. So there's an awful lot of material there, Craig.
And you got the date right.
Yes, I physically changed it before I put the slide up because I'm just such a nice guy.
Thank you.
And, yes.
Yeah, you didn't think I could get through 84 slides, did you?
I didn't think you could. You did a really good job. I was very impressed. And of course, when you're trying to present something that is basically amounts to a Bible of DB2 information in only an hour and a quarter, that's pretty darn amazing. So with that, I'm going to thank everyone for attending. Thank you for making us part of your day. And if you're listening on the replay, you'll hear the information. And there we go. But with that, I should start the music. And I'll thank you again, Craig, for a great job. And we look forward to seeing you next time on the Db2Night show on February 14th for LUW, and February 28th for the next Z show. Take care, have a great weekend, and we'll see you soon.